Hi friends, welcome back to the second video in the series of lectures on bolted joints. So in the last lecture we covered all these things. We covered what is a thread profile and the related terminologies like nominal diameter, pitch, crust, root, the concept of tensile stress area, all these things are covered in the last lecture. Then we went ahead and talked about different thread standards like the unified standard, then the ISO standard. Subsequently, we also talked about according to each of these standards how we can give a particular nomenclature to a screw thread which is having a certain nominal diameter and which is having a certain pitch. Then in that particular video we talked about the classification of thread profiles like the fine thread, the coarse thread, the multiple start threads, single start threads, and what is its implication on the lead of a particular screw thread. Towards the end of that video, we also saw the concept of tensile stress area and how handy it is when you are asked to compute the stresses on bolts. Moving ahead, in this particular video, we will look into the history of screw threads. When was the first time that screw threads were put into use and what was that, for what purpose they are used it? Then we will go and talk about the whole concept of mechanical advantage and then how it is used in the concept of screw threads. Then another very interesting topic, how this thing like when you have a mating nut on the screw thread, how it is equivalent to that of a block on an inclined plane. This is pretty interesting and that will lead us to the mechanics of power screws. So step by step we will uncover a lot of things in this video. In order to answer the question, who used screw threads for the first time or who came up with this particular idea of screw threads? The answer is this. So this novel concept is proposed by Archimedes in 3rd century BC. This works similar to a pump. So you have some amount of water at a lower height and you want to move it to a place where height is more or to a place of higher altitude. So what Archimedes proposed was to have a cylindrical structure inside which that will house a helical kind of structure or a spiral kind of structure as shown over here. Now what you have to do is you have to rotate this whole cylindrical object. If you do so, what happens is water from this particular point will slowly move and occupy the places in between these two spiral objects, and as it is rotated this water will slowly move up and reach this particular point which is at a higher altitude or at a higher height. So this was used to remove water from sinking ships. A very novel concept indeed, isn't it? Archimedes was indeed a polymath. And whenever we will talk about Archimedes, one of his famous quotes comes to our mind. It is this one. Give me a place to stand and a lever long enough, I will move the world. So this particular quote takes us to the next segment or the next topic in this video, the concept of mechanical advantage and lever. All of us have learned this in our high school classes. So here I have shown a simple lever. The total length of the lever is something like 110, let it be millimeters. Then using a 10 kilogram force at a distance of 100 mm from the fulcrum, we can lift a load which is as high as 100 kg, which is situated at a distance of 10 mm from the pivot. So it's useful, right? So the mechanical advantage will be something of the order of 10 because using a 10 kg load, you can lift a weight of something like 100 kg. Believe it or not, we make use of the same principle while we are tightening a bolt. Let's have a look at this. So assume that this is the axis of our bolt, and then this is the place where we are tightening it using a torque wrench. So if we are using, or if you are exerting a force that is equivalent to 10 kg at a distance of 100 mm, then we can develop a force that is equivalent to 100 kg at a distance 10 mm at the screw thread. So to give you a better clarity, I have another figure over here. See, have a look at here. So if you apply a 10 kg force over here, well, let's say A is equal to 100 mm, then at this interface, at the interface of the screw and the socket, there will be a force which will be generated, which will be higher compared to the force that you have applied over here, which will help the screw to move about the socket, around the socket. Make sense? But is this enough? Is it just this principle in action when you tighten a screw? No, not necessarily. Because when you look at the screw in detail, you see there is a small angle over here. There's a small angle over here. It is called the lead angle. This particular angle is called the lead angle. For the time being, let me call it alpha. So there is some more mechanics that comes into play. So what is that? For the time being, let's digress from the whole concept of screw threads. Now, go back and look at the good old concept of block on an inclined plane. Here it is. I have shown an inclined plane and I have an object over here, this one which is having a weight of W, which is kept on a floor which is on an inclined plane having a friction coefficient equal to mu, and I am applying an external force F. Is there any mechanical advantage involved over here? Just hold your thought for a while, pause this video, think over it and come back. Before I answer that question, let's have a look at how Egyptians built pyramids. Actually, they use this concept of ramps as shown over here. See, they are making use of a gradient as shown over here to pull very high masses to a height. So that's how they build this whole this big structures. As you can see over here, they have these ramps running all across to the top. This clearly indicates that when you use ramps of this kind, there is definitely a mechanical advantage involved in it. Now let's prove mathematically these arguments using a small block resting on an inclined plane with some amount of friction. So let's get started. So what we are going to do, we are going to evaluate what is the minimum F, which is the external force required to push this particular mass of weight capital W along this particular plane. Is the objective clear? We are trying to figure out what is the minimum required F. There is a friction. So if we perform a thought experiment, let's say I apply some amount of F, very small amount of F, then what will happen? The friction will oppose the motion. Friction at this interface will oppose the motion. And then when I'm slowly increasing the force, this external force F, at some point of time, this external force will be ample enough, or it will be good enough to make or to set this particular object into motion. So that is the F we are trying to find out. Clear? So the process is pretty straightforward. You want to write equations of static equilibrium in both these directions, in this x direction as well as in the y direction. I have taken my x direction in this way for easiness of computation, and y is of 90 degree perpendicular to this x direction as shown over here. This is how the free body diagram will look like. There are 4 forces acting on this particular body. Capital F, which is the external force that is acting on the body. Then W is the self weight of the object. This is the frictional force that is opposing the motion up the inclined plane. Then there is normal force which acts at the interface between the body and the inclined plane. Now summing up the forces in the x direction, we will arrive at this set of equations. I'm not diving deep into it in the interest of time. So this is equation 1. Similarly, when we sum up the forces in the y direction, we will get this particular equation. Now we have an expression for the normal reaction, and we have an expression for the frictional force in equation 1. Actually, if you remember we have learned that at the time of impending motion, that is the time at which the motion is about to start, the frictional force is related to the normal reaction by this expression. So we are talking about a moment where this particular object will start to move. So this equation holds true at this scenario. Make sense? Now substituting equation 1 for this particular term and substituting equation 2 for this particular term, finally we will arrive at this particular expression. So this is the minimum force required when you have an inclined plane of inclination theta and the friction between the object and the inclined plane is mu and weight of the object is W. So this is the amount of force that we need to apply to get this particular thing moving. Now what is mu? For explaining that, I'm slightly taking you to another thought experiment like this. I'm trying to explain what is angle of friction. Think of having an object resting on a plane surface. When you are up, this is having a friction of, let's say, mu again. So when you apply, let's say, a very small amount of force, the object won't move because of the frictional force. At some point of time, the object will start to move. That is called the point of impending motion, isn't it? If we draw the free body diagram at that location, it will look something like this. It will look like this, isn't it? So here I have the weight of the object acting, here I have the external force, and here is a normal reaction, and here is the frictional force. Now, corresponding to this time instant where this object will start to move, the frictional force is given by this expression. Make sense? Then, angle of friction is defined like this. Angle of friction is the angle between this particular normal reaction and this particular normal force and the reaction. Reaction is the equivalent of these two things. So reaction will be the component of this resultant force is one is F max and the other is the normal force. Okay, so this is the resultant force at the interface. So once again, angle of friction is the angle between reaction force and the normal. Make sense? Good. So in this case, when you're applying a smaller force, there is no motion. Then this particular angle which the reaction force makes with the normal is less than your angle of friction. But when this reaction force makes an angle which is equivalent to your angle of friction, then the object will start moving. Make sense? So that is the concept of angular friction. And I try to bring your attention to this very important curve where it is clear that when we are keep increasing the external force, on this axis we have external force and on this axis we have the friction force. So when you keep increasing the external force, there is a point at which friction force will not further increase. So we are talking about this point because as we are interested in to compute the minimum force required to move the block up the inclined plane. So that's why we substituted force of friction is equal to mu times the normal force. Make sense? Now let's go back to the equation and make a very important substitution. So we arrived at this expression from a lot of calculation. Now let's substitute mu as tan of phi s, where phi s is your angle of friction. Angle of friction. If you wonder how this expression came, let's think about it on your own and then come back. See, answer is pretty simple. I told you angle of friction is the angle which the reaction force makes with the normal direction. So when at the time of impending motion, okay, so if I take the tan of this particular angle, it will be opposite side by adjacent side, right? Because this will constitute a right triangle. So tan phi s will be mu n divided by n, which is mu. So tan of the angle of friction gives you the coefficient of friction. Make sense? So this particular substitution is justified. Okay, once we plug this back, now mu will be tan phi s, mu will be replaced by tan phi s both in the numerator and the denominator also. Then what we will arrive at this very important formula where we will say the external force required to move this object of weight W is tan of phi s W times tan of phi s plus theta. Make sense? Now, if we work out an example with numbers, we will get to know that this F will be, the minimum force required will be less compared to the W, which is the weight of the object. I will just draw your attention. We were solving this problem where we wanted to move this particular object, which is having a weight of capital W, up an inclined plane, which is having an inclination theta, using this force by applying an external force like this. Okay, makes sense? And if you wonder what is phi s is tan inverse of mu, where mu was the coefficient of friction between these two surfaces. Let's plug in some numbers to this particular formula and see whether it works or not. So here I have a question. A block rests on an inclined plane at 12 degree to the horizontal. So theta is 12 degree. The weight is 80 Newton, capital W is 80 Newton, and the coefficient of friction is 0.4. Mu is 0.4. Calculate the force that will just make it slide up the plane. Now, it's a pretty straightforward problem, so I'm not going to solve it in detail, but once you plug in all these numbers to this particular formula over here, then finally we will arrive at a number where F will be something like only 53.5 Newton. So weight of your object is 80 Newton, but you can make this object slide up the plane by applying a force of 53.5 Newton. So there is indeed a mechanical advantage. So let's sum up what are the key takeaways from this particular lecture. So we started this lecture talking about the history of screw threads. Then we established that there is mechanical advantage when we use a lever, and a similar concept is used when you're tightening a screw. Then there is mechanical advantage in an inclined plane that we just saw now. And the very important concept that I didn't explain, but which is an important takeaway from this lecture, is that force due to drive friction is independent of contact area, because we will make use of this particular concept in the next lecture when we talk in detail about the mechanics of power screws. Thanks for watching.